I'm going to tell you all about econ and game theory in blockchain. So I know you know all about econ, and I know that you know all about game theory because I saw Jonas teach it, and he did an awesome job. It was taught in the kind of traditional context, and which is great. And now we're going to see how some of those lessons that you learned from Jonas apply to like very specific scenarios in the blockchain industry. And this lesson, unlike most of mine, doesn't try to really like weave a narrative and like come up with a point at the end. It's actually just a look at example after example after example. And so let's dive in. So the goal of this lecture is that, like, by now we're all familiar with all of these topics, like, supply and demand and Nash equilibrium and strategies and all of that stuff. Shelling point, for example, and you also all have like a lot of blockchain content that Andrew and I have taught you like over the last few days. And so we just want to see how we can kind of like glue these things together. So the goal is to combine the two and see how like economics and game theory can be applied specifically to blockchain. And like I said, we're going to do a whole bunch of examples. So let's start with like a summary of how I'm going to be approaching this to like bridge the gap between the two modules. So we're basically going to treat systems as games. So you can think about like all of these different state machines that we've talked about or whatever your favorite blockchain system is, and we're basically going to model it as a game. The participants in those games, for example, are going to be like the miners or validators, or maybe they're just going to be like the users or the developers of the smart contract. So basically, like everyone who plays some kind of role in one of these systems is basically just going to be a player in our games. And by game and player, I'm using it in the specific game theoretic concept, like context, like Jonas was. And so we're going to treat protocols like the Bitcoin protocol or the Polkadot protocol as the rules of the game. And then we'll analyze them using the tools that we learned. And so we know that like when you're going to draw a game matrix or decision tree or really just analyze any game, you kind of need something to quantify the payoffs for different game outcomes. And in the last module, we just had kind of like an opaque notion of utility. We indicated that a lot of times maybe if you need to create incentives, just money is a good way to do it. And so now we're going to be using basically our cryptocurrencies as points or as our utility. So the way you win this game is you do whatever strategy you can to like accumulate the tokens. That's what we're going to say. Yeah, and then the rewards and punishments are the incentives. So the protocol rules will typically specify some reward for authoring a block or punishment for like including an invalid transaction in your block or failing to author or something like that. Okay, so let's take a look at markets. Hopefully that's pretty familiar. A market's a composition of systems, institutions, procedures, social relations, or infrastructures whereby parties engage in exchange. And markets are like the cornerstone of our economy. They're everywhere, which also means that they're like really thoroughly studied. We know a lot about them. That's good for us. So let's look at something that also might be kind of familiar. The Bitcoin fee market. This is the fee market over time. It's not all of Bitcoin, it's only the last couple of years. Or actually, it's just some random couple of years, now that I look at it more carefully. But we definitely have a peak right there at the height of the, the height of the block space demand. So, users bid with their fees in order to buy this resource called what? What's the resource that you buy when you're bidding with fees in the fee market, like in Bitcoin? Yeah, bingo, block space. Yeah, that's exactly right. So the product being exchanged is block space, and the miners are producing it. And effectively what's happening here in the fee market is that there's an auction to see who can buy block space. Now, markets, like this is a really volatile market. Like look at that. We have this spike here where the value of the fee market like triples and then thirds over just a couple months there. So it's a really extremely volatile fee market and way more volatile than you typically see in most markets for normal products. If you think about anything from a consumer product like toilet paper to a commodity like oil, this is like pretty remarkably volatile. The fee market changes a lot. Or I should say the price for block space changes a lot. And so why is that the case? We learned from Jonas this concept of market equilibrium. The transactions that manage to get into the blocks have fees representative of the current market equilibrium. So this is like, we see here the law of supply and the law of demand. So yeah, actually this doesn't have axes labeled, but can anyone tell me like what is this graph? Do you recognize it from Jonas? Like what should my axes be here? Go ahead. So well, the lines represent supply and demand, but what are the axes? Yeah, available amount and price. Yep, and so we know that like as the price goes up, typically what is the green line? Yep, as the price goes up, suppliers are incentivized to supply more, and similarly, as the price goes up, if you're a consumer, you might be demanding less because you can't afford it or you don't want it at that price anymore. This is what normally happens. And the red line, the law of demand, is perfectly normal, perfectly the same in blockchain, but the green line is actually a little bit weird. What normally happens if the price of oil goes way up is that producers are going to produce a little bit more oil, take advantage of the high prices while they can. But block space is, so just wanted to say this too also, like in the extreme cases, when the demand gets too high, when you get to that peak in the graph, the price can be so extreme that normal users of the network don't want to use it anymore. And so for example, there used to be this contract called BTC Relay that ran on Ethereum. It's basically like a Bitcoin light client that ran on Ethereum, but it takes a lot of gas to update the latest Bitcoin block header into the Ethereum blockchain. And when the fee price on Ethereum got too high, no one wanted to update BTC Relay anymore, and the whole light client and bridge that was built on top of it stopped functioning, and that's because the economics of the fee market weren't compatible with it. So we got to figure out why this is, and we got to figure out why it's different than normal markets. Go ahead. Yeah, pass the mic right over you. Marcus, throw that mic behind you.
How is that different?
Like, yeah, I haven't told you yet. I'm teasing it, right? I haven't. Oh, you don't see how it's different? What's different is that
because like basically like if the price goes so high, like so at a certain point, like the demand is like in the normal graph, when the price is very high, the demand is very low,
zero.
Right?
Yep. So the demand side works the same way. The demand side is the same. It's the supply side that's different. So here, let me just tell you, let me stop teasing it. So it is typically not the case in a blockchain network that adding more miners or more validators creates more block space. That's not the case. That's totally different than everything else. If I add more toilet paper factories, that makes more toilet paper. If I add more oil wells, that produces more oil. But in blockchain, at least in most of the blockchains today, especially the early ones, adding more validators or miners doesn't produce more block space. It just makes the existing block space, or I should say, it makes block space more secure, but produced at the same rate. And so it's not really, sorry? Yeah, so if we could increase the supply of the block space, then it would behave more like a normal market. And so some more modern blockchains are trying to do that. So like, for example, roll-ups or parachains are all ways to try to like increase the quantity of block space as opposed to only the quality. Now, quality is extremely important, right? I'm not saying that quality is not important, but it also doesn't make sense to have the quality of your block space varying drastically over time. It probably makes more sense to let supply increase with demand.
I just want to add quickly that it's not fundamentally different than normal markets, I think, because I think the concept also exists in normal economy that like it's a bottleneck. For example, Suez Canal, there's a finite amount of like
a certain amount of bandwidth. You can only fit so many ships through per day. That's a great point.
During COVID, there was like a bottleneck.
Yeah, very good. Yeah. Very good point. Yep. Yeah. What do I mean by quality was the question. And I was referring to quality of block space. So Andrew mentioned this a little bit earlier. Quality is a little bit of a It's not a totally precisely defined notion, but let me give you some intuitions. High quality block space will be predictable. You'll have a regular block time. You'll know that your chain is going to stay live. If your chain doesn't stay live, that's not really high quality block space. You'll have a lot of validators in a lot of different geographies and a lot of different political jurisdictions and things like that, so that you know it's unlikely that there'll be collusion, for example. If it's proof of work, you'll have a lot of mining power. Or if it's proof of stake, you'll have a lot of stakes slashable locked in the system. And the reason that that makes the block space high quality is because you have this little guarantee. You know that if anything goes wrong, someone's getting slashed and paying a lot of money. And therefore, they're incentivized to not have anything go wrong. So that's what I mean by high quality block space. So I think the exact example that Andrew used of really low quality block space is like, maybe he and I get together and spin up some random shitcoin and we're like, yeah, deploy your contract on here. And you're like, that's not high quality block space. There's only 2 miners and you guys are friends and you can easily like collude to censor me or whatever. Does that answer it? Thanks. Yeah, so here's CryptoKitties, right? This is actually the same point that we were just on. Let me see if I didn't say any of this yet. So actually, some blockchains early on did try to implement like variable size blocks. It's not always the easiest thing, especially when you're first bootstrapping a network, to do that, because you kind of want to have basically what I'm trying to say is like, if you were to do this in Bitcoin, let's say we wanted to keep the difficulty fixed so that when more miners join the network, it doesn't get harder to mine. You actually just get blocks faster. You're also like affecting your block time, so there's some trade-offs. So you have to be like kind of clever when you're trying to design these like dynamically scalable block size systems. Another way to do it would be to maybe change like the size of the block dynamically. So Ethereum actually does that a little bit. There's like the target gas per block, but it can go like higher or lower. Okay, so that's the one about fee. That's my example of fee markets. It's the mempool. Any question about fee market application? All right, let me move on to the next one. Okay, Nash equilibrium. So here's one from game theory. See if we can predict what users are going to do. So here's what a Nash equilibrium is. Remember, it's the strategy from which you don't want to deviate, because if you deviate, you're going to do worse. Once we're in a Nash equilibrium, if any player individually changes their strategy, that player is going to do worse, and therefore nobody wants to do that. So what is what's the strategy for BTC mining? Hopefully, the equilibrium is mining honestly. That's what it would be if we've designed our incentives correctly, right? If we have a good, sound crypto economic system, then the best strategy should be the honest strategy. But let's not just take my word for it. Let's actually see what the Nash equilibrium is. So here's our game matrix. I'll start to fill it in, and we've got, we'll simplify it a little bit and just pretend there's 2 miners. And to make the math easy, we'll say the block reward is going to be 2. So every time I mine a block, I get 2 new Bitcoins or 2 new tokens. And the difficulty scales with the number of honest miners. The miners are rational actors. So what I'm saying here is basically they want to earn as many Bitcoins as they can. That's their goal. That's their utility function. And the dishonest miners don't cooperate or don't follow the protocol or behave however they want. So let's figure out how many tokens each one of the miners will earn in this setup. So if both miners are not mining honestly, none of them produce any valid blocks, and there are actually no Bitcoins being mined at all. So they don't get any tokens. If they both mine honestly, we'll say that they typically get about half of the reward, right? Maybe we'll assume they have equal mining power. So if miner A is mining at some rate and miner B is mining at some rate, of course there'll be periods or sprees where one gets ahead of the other, but typically they're mining at the same rate, and so they pretty much split the rewards evenly. All right, so let's see what happens in the other cells here. So if we have miner A mining dishonestly and miner B mining honestly, then of course miner B gets all the tokens, and it's symmetrical on this side as well. So who wants to analyze the game matrix for me? Do you see any Nash equilibria there? Let's see. So it's maybe might look similar. This is certainly a good outcome where they both get a reward. But the cooperation game is like the cooperation game. I was thinking the coordination game. Wait, what's the cooperation game? Oh, coordination game. Okay, yeah. So it's not quite, because in the coordination game you have like, this is a good outcome for everyone, and so is this. But these ones where they play different strategies aren't. What? Somebody say something? Anti-coordination.
I think there's two Nash equilibriums here, like, because basically, like, if both play honest, then each gets one. If and if both play dishonest, then like they get either 2 or 0, but like the chances you might say are 50-50, and therefore they get 1 over time.
All right, let's do the analysis like this. Let's pretend that miner B is going to mine honestly, okay? Pretend we know that for some reason right now. We'll just consider that. And so we are miner A. So we have a choice whether we want to play this strategy or this strategy. So and this is our payout, like here in the bottom left. So can we do better by switching from honest to dishonest? Yeah. No. If we switch from honest to dishonest, we go from 1 token to 0. So that's bad. This is this isn't how Jonas drew his matrices, is it? He did like the 1, 1 notation. So this payout here is miner A's payout. And it makes sense, right? Like, let's look at this square. For sure we know this one, right? Like if one mines honestly and the other doesn't, like the dishonest one gets 0. Yep, okay, good. So we know that when miner B is mining honestly, definitely miner A wants to do that as well. So now let's look over here at when miner B is mining dishonestly. In that case, what does miner A want to do? Hooray! That's good, right? That means our incentives work out. That means that the best strategy in the Nash equilibrium is for both miners to mine honestly. That's how they do the best they can. So the meme is true. Yeah. Get the mic over here. Who's got a mic? Here it comes. You ready to catch? Yeah, you can do it. You can do it. Oh, nice, okay. Very safety first, risk averse with the throwable mics.
So I'm not questioning. Hello. Yes, okay. So I'm not questioning the Nash equilibrium, but I want to know in a case where, like, let's say there's multiple miners, but it starts from 1, 2, 3, and then exponentially the numbers grows. So in this case, for example, if there are just 2 miners, then you technically might not know what is the dishonest one. So,
this is a great question. You're sort of getting at like the semantics of honest and dishonest, right? You're saying like there's just 2 miners doing different things. It's kind of arbitrary.
How would you know like what is honest, what is
honest? That's actually my next example. So great question. Let's get to that. For this part, at this moment, I'm kind of assuming that there's some very clear notion of what's honest and not. Okay. And in the real world, I think that's pretty clear. Honest means like, follow the Bitcoin protocol the way it's written in the published software and everything. But your point is like fundamentally correct. Absolutely. So great thought. Okay, so actually let's do yours right now. So that brings me to network effect. So the network effect of a business principle is a business principle that illustrates the idea that when more people use a product or service, its value increases. So you can just think of like a social media platform, for example. If I spin up my new, I have a concrete one. I saw this one called Space Hay being promoted recently. Has anyone heard of it? New social media network. It's like designed to look like MySpace and feel the same as like vintage MySpace from like 2005. And I like loved MySpace in 2005. And I was like, yes, I am going to be all about Space A. And then I get on there and I'm like, oh, no one's here. I'm like posting for myself. This is a useless social media platform. Like, even though I kind of don't really like Twitter, like that's where people are going to read my tweets, right? Not here on Space Hay where no one's looking. So that's like a classic example of network effect. And it's going to apply perfectly to Bitcoin as well, because if I have my little cryptocurrency over here that no one's using, no one's going to want to get it. No one's going to want to buy my token if they can't spend it anywhere, for example. But if we're talking about like Bitcoin or ETH that have kind of already started to overcome these network effect problems, they're really valuable. Sometimes people say like, the value grows like quadratically with the number of people, but it's not really important exactly what the function is. It's just that it gets more valuable as there's more people. So we're going to do basically the same analysis as before, and here's all of our same assumptions that we had before, but here's the new one that we're going to add to sort of like address the network effect I see you kind of looking around the podium. Sorry about that. So the token price scales quadratically with the number of honest miners. And that's exactly what I said. Like, Bitcoin has a good price because a lot of people use it, and my shitcoin has a crappy price because no one wants to use it because no one does use it. And so we're going to equate some like real world value to the tokens that they're winning. So if there's only one honest miner, if there's only one person, a small group of people using this network, then we'll use like dollars to represent our real world value. Actually, I didn't make this slide because I never would have chose dollars there. I would choose like hamburgers or something that's not a fiat currency. And then if there's two honest miners, or if the group grows, then the real world value of the tokens is also going to grow, and it's going to be like quadratic. So the 1 squared becomes 1, 2 squared becomes 4, and this shows how the value of the network increases. So let's look at our game matrix again. So the bold numbers are what we always had before. This person's going to get 1 and 1, or here we're going to get 2 and 2. But now we're also adding in the part that reflects the network effect. So up here in this square, we have 2 honest miners, and so our token value is going to be 2 squared. Here we only have, and same here, we only have 1 honest miner, and so our token value is going to be 1 squared. A smaller network has less token value. So let me just simplify the math a little bit there, and a little bit more. And so here's our final game matrix. So what do we see? What's the Nash equilibrium? Still be honest. And is it a sort of like a stronger or weaker Nash equilibrium? Yeah, absolutely. And what I don't know if Jonas sort of introduced that or even if it's a real concept, but what I'm trying to get at is like, if you were to move away, you have more to lose. So it's a more sticky Nash equilibrium. If it's kind of like a weak Nash equilibrium, you can think of it as trying to like climb out of a small hole. Like maybe I just kind of like jump up and then I'm out. But this is like a deep well. It's going to take a lot to get out of that. If it's small, I might be like, yeah, I know I'm going to technically lose money by switching, but maybe I'll just try it for a little while and see if other people switch strategies. But now we have a very strong Nash equilibrium, and if I switch away from it, I'm going to lose a lot of money. And the bigger the network gets, the stronger that effect gets, and so it actually becomes more and more incentivized to continue mining honestly. Yeah, this time I animated it. Should have done that last time. So there's our Nash equilibrium. Yeah, go ahead. Let's get the mic back here. Here.
Hi, Sukhmeet. So honest and dishonest, right? Like, so mining, the idea of it does not correlate to Nash equilibrium because I was thinking everywhere there is fraud is because it's easier. So value would be more, whereas it says 2. So its value should be 8 or the input should be very less. Otherwise it would not make sense to be for somebody. It's like saying, if you are a good boy, you will pass. But not everybody is a good boy, right? Like, or they cheat and still pass. So they work less.
What we're seeing here is that if they cheat, they don't still pass.
Yeah, because of the values that you have put in, right? If input is far, far, far less for a cheater than on being honest, then they would rather cheat and win. No?
What do you mean by input?
Anything in that Nash equilibrium, whatever is the resource. If resource is important, then that would correlate to the price that you put in as quadratic equation. So
okay, I'm not quite getting you, but I like that you're engaging with it. So let's dig in a little bit afterward. Thank you very much.
okay.
Yeah. Okay, so now I'm going to get to the point that you were asking about like what does it really exactly mean to be dishonest? Oh, sorry, did you have another question? Yeah, all right, pocket over here. Got it, thanks. Arms up. Nice.
Okay, you made a very interesting point, and I'm just curious on your thoughts, right, as it relates to research too. You mentioned something in regards to Bitcoin having utility versus, I think meme coin or shitcoin not having any utility. But I mean, whenever a network starts, right, doesn't the utility not exist? So does this entire concept account, I guess, for future expected value? And to elaborate, right, I'll give two examples. currently we have something called Celestia, people, data availability, right? Only 0.1% of the actual, I guess, capacity of this, new data availability is being used, but the token is valued at like multi-billion-dollar FTV, right? So it means that it's barely being used. Whereas, Bitcoin is currently used, but then you also see something with like meme coins where they end up going to like 10, 20 millions, right?
Yeah, so in the game theoretic model, I mean, it sounds like you're sort of distinguishing like the actual Celestia users, like the people who really have data that they want to be available, as like the real players in this game. But there's a lot of other players in this game, including the coin traders and speculators and everything. And so it might just be that, a lot of people are speculating on this one, and there's deep liquidity in the markets, and so therefore like those are more the players really than the data availability stores. But I also want to just like latch onto your point that like when you start a new network, it has no network effect, and that is a huge like hill to overcome. That's extremely hard, and so that's, like, okay, so back when Bitcoin and Bitcoin Cash first split off, it was kind of like reasonable to debate like which one's going to be the real chain. Let's like have a hash war and see. Nowadays, it's pretty clear that BTC has won, right? It has the network effect. So even people like me who were sort of big blockers would never deny, like would no longer say like, oh, Bitcoin Cash is like the real Bitcoin or whatever, because the network effect is there. So yeah, and I honestly don't really feel like I have a good theoretical model of how you overcome that initial network effect or like how Bitcoin did it. Maybe like the cypherpunk in me says it's like, yeah, it's because it was such a great idea. Everybody just knew. But I'm pretty sure that's not it. So I don't know how you
Thank you.
strap
It
things.
feels like a multi-agent game, right, that is being played currently.
Yeah, definitely a multi-agent.
All right,
Yeah.
thank you very much.
Yep. Okay, so let's dig in on what it means to be honest versus dishonest. So there are some like mainstream rules, and if an individual miner breaks them, then that's kind of like what I was saying. That's like cheating or being dishonest or whatever. But if multiple miners break them in the same way, it can kind of just be seen as like a new protocol that deviates from the first one. So Bitcoin Cash, for example, or like when the main Ethereum chain changed its rules to do the DAO fork. So like you can think of Ethereum Classic as like the original rules and ETH as the fork one, because all of the miners started to break the protocol in the same way at the same time. So let's try to see what happens here. I've no longer named my columns for my strategies honest and dishonest. I've now just named them Bitcoin and Bitcoin Cash. Okay, it's not that either one of them is honest or not. It's that we have a difference of opinion here, and we need to fight it out. It's not going to be just one person mining on the other chain doing their own thing. There's a lot of people coordinated here. And remember, they actually are both experiencing network effect as well. So if everyone's mining on BTC and very few people are mining on BCH, BTC is going to be worth a lot more, and vice versa. So here's the payoffs. It's sort of like the same as before. If both people are mining BTC, the total 2 BTC reward gets split between them. And if they're both mining BCH, then the total BCH reward gets split between them. Now over here, this is, if you're mining BTC and the other person is doing this dishonest thing, you see this as 2-0. But if you're a Bitcoin casher, you see it as you being honest and the other person getting 0 Bitcoin Cash. And yeah, sure, they got this other token, but that's not the real one, That's the argument that both sides are making here. And so there's no actual zeros anymore. There's no you get nothings. You're always going to get something. You're going to get the token of the chain that you're mining on. And in order to figure out what the Nash equilibrium is, we need some way to compare the real world values of these things. So let's just add in our network effect numbers again here. Just like we did before. When both people are mining on the same chain, there's a big network effect, so you do 2 squared. When only one person's mining on the chain, then it's 1 squared, much smaller effect. So we'll simplify, and now that is very interesting. So what kind of game is that? Coordination game. Bingo, now we've got a coordination game. Oh yeah, okay, come on. That's how there's the analysis. There's our 2 stable Nash equilibriums, and that is, like we said, the coordination game. So, is being honest the best strategy? Not always. If the majority of people are honest, then honesty pays off. If the majority of people are dishonest in the same way, then being dishonest with them pays off. But with them is important. If everybody's doing their own random dishonest thing, then you need to get with the biggest group. That's the thing. That's the way to pay off. So if there's a big group being dishonest together, you can, join that crowd. But you can't, it's not just like you can all be dishonest in your own disparate ways, because then you would just have 1,000 little low cap coins. Throw it up here first, then I'll get you. Right up front. Where's the mic? Marcus, chuck that mic. Yep, you got it. Nice.
So this would lead to a winner-takes-all situation.
Or at least winner
Blockchains?
takes most. There'll always be some people who are philosophically still on the other side, but yeah, that's right. Because, and it kind of happens, let's say at first we have like this arm wrestling match, things are kind of even, but once it starts to go one way or the other, then you kind of have a runaway effect. Once it's clear that one side's starting to win, all of the rational actors on the other side will say, okay, I'm losing, I should switch back to the other one, or switch to the big one to get
If they are rational.
if they,
right?
yeah, exactly. Yeah, if they have. And what I mean by rational here is that this payout matrix actually models their utility. And it might be the case that they care more about making the I value big blocks statement than they care about earning the money. And some people are like that. Yeah, hawk it back there.
So in a sense, we can get rid of the dishonest terminology and
Yeah.
just say narrative, chain, like which
Absolutely.
fork, which
Absolutely.
yeah.
I think anytime there's a concerted effort to do something different than the protocol on purpose, then it's like a little bit more.
Narrative, I think.
Yeah, narrative is a better
following
fit. I
the
still think
sapiens.
honest or dishonest, like words like dishonest or buggy or faulty are still okay when it's like an accident or like, you're not trying to fork off or something.
Yeah.
Yeah, I agree. All right, back over here.
So is that an inherent risk of POS? Because I can understand POW is mathematically proven that it is secure, but it seems like POS is a lot of this game theory, and there's this assumption that number one, everyone actually work rationally in terms of maximizing their money. But in the world where there's a lot of polarized opinion, people may actually choose an option that may not be the best monetarily, but then once a lot of people actually choose that option, it can disrupt the entire POS. So for example,
The entire POS?
so the entire proof of stake concept, because the proof of stake assume that everyone actually work rationally. But if, for example, in this world, there might be a day where a lot of people on the network actually hates a country, and then they do something that may not be rational initially, but then when enough people actually do it, it actually destroys the whole concept of the blockchain.
Your point about rationality is correct. Like, we're assuming that our game matrices model the incentives of the players, and if they don't, then the proofs that we generate from those game matrices won't apply to the real system. That's true. But I think that this model applies equally well to proof of work and proof of stake. I don't think it's different there. Because, here I'm talking about mining rewards, but you can just think of like staking rewards, right? So if I stake dishonestly, then I'm going to get slashed on the, I don't know, like whatever. These are proof of work chains, but I'll get slashed on the one chain, but then I'll get the rewards on the other chain that I'm mining honestly on. So I think the model works for proof of work and proof of stake, but your point about rationality is well taken and is correct.
Sorry, I thought proof of work is you need to solve that mathematical model, right? So meaning that if I'm even on a dishonesty, there's no way that I can solve it. Whereas
Well,
POS,
okay. I'm not talking about I'm not talking about like cheating on the literal proof of work. What I'm talking about is like, let's say you and I get together and we say, we're going to start our own chain and the proof of work rules are different. Maybe we have a different difficulty threshold or something. So we say we only have to mine blocks with 3 zeros at the beginning, but the old chain requires 4 zeros at the beginning. So they would reject our blocks as invalid, for example. But it doesn't have to be, and often isn't, about the consensus rules. It could be totally orthogonal to that. Like maybe we're forking over some political issue. Like maybe this side of the chain wants to sanction like the names that are on the OFAC sanction list. And this side doesn't. That stuff all happens in the state machine, and you can still totally do this fork and this analysis. Thanks for your questions and thoughts. Yeah, okay, we talked about that one. Okay, shelling points. So a solution that people tend to choose, the one that's easiest to coordinate on, that's what we call a Schelling point. And it's often the case that they're also Nash equilibria. So let's see, how is this useful in blockchain? So here's a game or a story that you can think of. There's two partners in crime over there, the masked bandits, and there's a detective that's going to interrogate each of these two sort of individually and get their story straight. And the game matrix, you could model the game matrix like this. So the truth is that these two are criminals and they're guilty, but there isn't very much evidence against them, okay? So if they both lie, they're going to get off the hook because they can't get convicted. But if they confess, obviously they're going to get convicted. And if either one of them rats out on the other one, they're going to get convicted. It's not quite the prisoner's dilemma because there isn't this like incentive for ratting out your other person, but it's similar. And the idea is that the only way for these two bandits to sort of trick the detective is to coordinate on a lie. And I have a little clip that I want to show you guys here that's relevant to this one. Okay, I don't know what the volume is going to be like exactly, so I'm just going to be like prepared to. Whoa, man, I'm going to try to be prepared, but honestly, like the mouse is kind of. All right, just bear with me.
How did they find out it was us that TP'd that house? Will you relax, Kyle? They've got nothing on us. As long as we all stick to our story, we'll be fine. We better go over our story again so we don't screw it up. Okay. Last night, all four of us were at the bowling alley until about 7:30, at which time we noticed Ali Sheedy, the goth chick from the Breakfast Club, was bowling in the lane next to us, and we asked her for an autograph, but she didn't have a pen, so we followed her out to her car, but on the way, we were accosted by 5 Scientologists who wanted to give us all personality tests, which were administered at the Scientology Center in Denver until 10:45, at which time we accidentally boarded the wrong bus home, and ended up in Rancho de Fritos Rojas, south of Castle Rock, and finally got a ride home with a man who was missing his left index finger named Gary Bushwell, arriving home at 11:46. I'm confused. Did Ali Sheedy take the personality test? Yes, dude. Kyle, it's very simple. We followed Ali Sheedy out to her car, but on the way we were accosted by 5 Scientologists who wanted to give us our personality tests, which were administered at the Scientology Center in Denver until 10:45, at which time we accidentally boarded the wrong bus home and ended up in Rancho de Fritos Rojas, south of Castle Rock, and finally got a ride home with a man who was missing his left index finger named Gary Bushwell, arriving home at 11:46. You got it? Oh, for Christ's sake! Look, Kyle, just let Cartman do all the talking, okay? He's better at being in trouble than anybody. Thank you, Stan. Shh, here they come. And so I said, that's a terrific joke, Wendy. Tell us another one. Oh, hello, Mr. Mackey. Are you ready to see us now?
We're going to talk to you one at a time, boys, okay? Kenny, will you step into my office, please?
No.
Come on, Kenny, let's go.
Touche, Mr. Mackey, touche. Why are they doing this one at a time? They want to see if we mix the story up and see if somebody will rat out the other 3 for a better deal. I can get a better deal?
So ChatGPT actually did not help me find that clip, but I appreciate whoever tried to help me with ChatGPT when I posted that on Discord. So what did you guys notice about Cartman's cover story? Anything? It's very complex. It's especially detailed. And I think that the reason that he did that is because he's better at being in trouble than any of them, and he understands that the game matrix actually looks more like this. It isn't just a matter of deciding to lie. He knows that if they tell inconsistent lies, they're going to get caught. If he says that they were bowling until 7 and then went out to get the pen and everything, but at the same time, like maybe Kenny says, like, oh yeah, we were like over at the skating rink and then, you know, something else, then Mr. Mackey's going to know, okay, you guys are lying, so obviously that's enough to get him in trouble already. And so the idea is that in many situations, you actually need to be coordinated with each other. The main thing you want to do is coordinate, and it's the case that the truth is a natural Schelling point, because you don't need to get your story straight if you're going to tell the truth. You all lived it, you all saw it, and all you have to do is say what you saw. You don't have to do all of this coordinating. And so it actually is relevant and comes into blockchain in the case of like oracles, for example. Okay, wait, I lost my speaker notes. So hang on one sec. All right, here they are. Okay, so let's think about what a blockchain oracle is. An oracle is a thing that requires, or not requires, but like tries to get some real world data out of the real world and into the blockchain so that then all of our on-chain logic can operate on that data. So just to give you an example, maybe we want to like measure what the temperature outside was or something. And we want to get the information about what the temperature was into the blockchain. Now, we definitely don't want to just trust one person to put that data in. That is, hopefully, by this point, it's clear why that's not a good idea. So instead, what we can do is we can allow anyone to participate in this protocol, and we can incentivize them for participating. Oh, yeah, so here's like some other examples of what we might do. And so we'll just use the temperature one as an example. And so if maybe you have a garden out here, wherever we're like measuring the temperature, and so you want to participate to earn a little bit of money by supplying data into this oracle. And let's say like you and a bunch of other people do that, and here's how the data come out. Here's all of the data that people said the temperature that I measured outside today. So what do you think the temperature was? Yeah, probably somewhere right around here, maybe somewhere in this region. And maybe this person is trying to trick the oracle. Maybe that person took a position in a prediction market betting that it was going to be cold that day, and they know that they're about to lose their bet, and so they want to trick the oracle and make the oracle think that it was cold, so they win their bet. Well, the thing is, there's a lot of other people participating, and it's naturally easy for those people to be coordinated. So if you want to coordinate to trick the oracle, you basically have to get enough people in your group and coordinate with you on the exact same lie. Luckily, it's easier to coordinate on a lie about temperature than about where you were last night, because it's at least like a one-dimensional real number. But you need to get enough people in your group to coordinate down here to overpower the people who are just going to naturally tell the truth. And the way that we can set up the incentives for this kind of thing is that we can pay the people not only for contributing, but for coming up with data that's nearby each other, by coming up with data that's close to the ultimate accepted answer. And that way, the people know that what they need to... So what we do is we set up a game, and the game doesn't actually inherently have any rules that know or enforce that you submit the real temperature. The game doesn't know the real temperature. It couldn't possibly enforce that. But it relies on this Schelling point principle to say, all I need to enforce is that people are coordinating and telling me the real thing, because it knows that the easiest thing to coordinate on is the truth. So this is one example of how we can use Schelling points in blockchain. Okay, questions about that one? Yeah, go ahead, mic up to here. Right behind you.
Okay, but what's the benefit of actually telling the truth?
Well, the benefit of telling the truth is that you get paid. These people are going to get paid.
So okay, it's just coordinating because, yeah, that makes sense.
So if I wanted to lie and I say this number or something, I'm not going to get paid because I'm too far away. Now, if I can somehow get everybody to lie with me, that's great for me, bad for the oracle. But I don't even know who those people are. There might be a lot of them. Some of them may have like moral notions of telling the truth, or some of them may actually have like the opposite position in the prediction market. So it would be quite challenging to get like a quorum to deviate from the Schelling point, is the idea. And the bigger the set is, obviously, the truer that becomes. If it's only 3 people, it might be pretty possible. Horatio. Chuck it. Yeah, you got it. Nice.
Yeah, Marisha. So, yeah, so concerning oracles, right?
Yeah.
And one thing about oracles, like they dictate other application, right? For example, DeFi lending and stuff, and other markets. So one thing is, if there's a situation, right? Maybe 2 teams are playing, right?
Okay.
And we, like all people here, maybe like 2/3 we bet on, let's say, Chelsea to win, and then
Yeah.
we lost, right?
Yeah.
And like we want to get the money, right? But then we as many we bet on Chelsea, but then we lost, but then we still want to get the money, and
Yeah.
we want to kind of trick the oracle. So
Yeah.
we will be majority, but we will still be wrong, and the
Yeah.
minority will be right, but then they'll be small. So
So it sounds like you're describing a scenario where all of the people contributing to the oracle are also all the people who are betting on the result of the oracle, and that is a little bit what should I say, like mixed incentives there, I guess, right? So I think it might break down in that case. I actually don't know exactly how you protect about that. That's a good idea. I think in the real world, typically what happens is that the oracle's participants are like not usually the ones betting, but I don't know if there's any way to enforce that. So yeah, that's something to definitely look into. Yeah, great thought. Oh, okay, yep.
We are working exactly on this scenario with Zeitgeist. Fundamental of predictive markets in like what we understood for last 6 months is Oracle cannot be participating in the predictive market that they are on Oracle for the bias nature.
Well, yeah, I mean, of course you want them to not be participating, right? But how do
Yeah.
you enforce that? That's
Because
the crux of it.
yeah, because it's a predictive market, either it's paramutual or not paramutual. It's very simple. The same addresses would not be in the Oracle list, right? Otherwise,
Yeah, but no, address, that's not nearly that simple because I can have two addresses. You know, like it's not Sybil resistant.
yeah, but
So,
their
yeah.
SDK allows you to question the Oracle later, so
Okay.
they can get punished.
Okay. Nice. Thank you. Okay, so what do we do with these attackers? If they go unpunished, they can definitely repeat that attack again, and eventually they might recruit enough people that they're successful. Or even worse, you know, maybe they can make a bunch of fake identities and spam incorrect votes or something like that. So we have to give these incentives, something that encourage person to do something. And I heard someone yell out the slashing, and that's exactly right. In our case, we want to shape the incentives that motivate the user to submit honest values. Oh, what happened there? Oh yeah, I think a slide got dropped, but yeah, slashing, that's exactly right. That's what we want to do. Yeah, so Sybil attacks is what I had just mentioned also. I want to go on to the next one. Oh my gosh. There it was, punishments. Yep. So we have this point here, the same point that Andrew made about the block authoring process earlier. Why would anyone want to participate in the first time? So someone yell it out. What? No, the exact opposite of that. Okay, altruistic maybe, yep, but what's a more likely one? Money, yeah. So we have to reward these people. So if you want to run an Oracle, you need to actually have some income like stream. So you probably need to charge your user to use the Oracle, for example. Okay, yeah, this is much more detailed than I remembered. Yeah, okay, so let's talk about state storage. So Ethereum's a blockchain that has all these smart contracts, which are little programs, basically little mini state machines. And the logic of the state machine is all stored on chain. They can be executed by anyone. And for them to work, a bunch of code needs to be deployed onto the chain, right? You have to like put that code into the chain initially. And then it gets replicated to all the different nodes in the system, and multiple nodes store the data on their hard drive. So Ethereum deals with the burden of replication by charging like gas, basically, for when you submit bulky data. All of that is on top of the normal computational costs. So you think about like calling a transaction on the Ethereum blockchain, you have to pay some money for all the compute you do. In addition to that, if you're going to occupy storage, if you're going to add stuff into the state, you need to pay a deposit on top of that. So whatever you put into state needs to be kept there because this particular piece of state might be relevant to some future transaction. Someone's going to come along and call some transaction in the future, and you don't know if it's going to need that state. So therefore, you have to keep every single piece of state. So let's look at an example here. Meet Bob. He's a developer. He happily deploys his awesome contract. He puts it on Ethereum. He definitely paid a hefty gas fee to put it there, but so be it. His code was added to the state, and now many nodes hold a copy of it. And then here's the problem. Like maybe later on, Bob decides to become a musician. He just wants to go play his guitar. He doesn't really care about his smart contract or Ethereum anymore. He just kind of forgets about it. He's jamming with his band. But the chain doesn't know that. His code still lives in the state just like it always there, and it has to be there because as far as Ethereum knows, anybody might call this transaction in the future. And to make it worse, there's a whole lot of people like Bob, and maybe some of them can continue like to work on their contract even. Maybe they're not like going off to play their guitar, they're just like writing the next version of their contract, and then they deploy the next version and the next version and the next version. And they never clean up their own data. Why would they? They already paid for it. So does anyone know an answer or have an idea about like what we could do to design a system better here that might make people want to clean up their contracts? Yeah, okay, go ahead.
Yeah, maybe like the Solana approach where you need to, it's account based, and you just throw to the processing runtime what is needed.
Say it one more time.
Like on Solana, it's not all of the data at the same time, it's just the data relevant for that processing moment.
Okay.
Do
Okay.
you get it?
It sounds like maybe you're saying you don't read all the data at the same time.
Yeah, exactly. Like you
But
don't
when
need
a
to
future
load everything.
transaction comes on, it might, like you can't just delete a contract off Solana, right? Because someone might call it in the future.
Yeah.
Oh God, really? Okay, I don't know how
You need
Solana
to
works.
pay
How does that
a-
work?
You need to pay a rent.
So tell me about it. Somebody tell. Yeah, throw it up here to you. Sounds like. You can just delete it. Yeah, that sounds cool. Oh man, hey!
Yeah, so yeah, I was actually going to ask if you're asking whether why we should remove it or not remove it, but I think within the Ethereum or traditional blockchain world, we don't want to remove a contract or any account details because of perhaps future programs or autonomous, programs would want to
Yeah.
interact with it.
Yeah.
But as he mentioned, yeah, in Solana to kind of avoid bloating
Yeah.
of the quote unquote chain, they allow you to remove like programs because programs are not like in Ethereum that are stored both the state and
Well,
logic.
but what under
Yeah.
under what context though? Like I can't just like call up Solana and be like, hey, delete this guy's contract.
Well,
I don't
no.
like it.
So like they have this notion of rent. So-
Rent, state
Yeah,
rent. Okay.
state
Yeah,
rent,
state rent is a good
exactly.
idea. I didn't
Yep.
know they did that, but state rent's a great idea. So you have to pay like every so often or something as
Mm-hmm.
you're occupying state. And if at some point you don't pay your rent, you get evicted. Is that the idea?
Yep, that's right.
Perfect.
Validators can kick you essentially out. Stuff
That's a
off.
great
Yeah.
idea. I didn't know Solana did that. That's cool. Does anyone know the way that Ethereum does it? It's sort of similar, but not quite the same. Yes, I heard someone say refund. That's exactly right. So the way it works on Ethereum is, so in Solana, it's like you're paying a fee for the privilege of occupying this state, and that's it. That's the expense of it. In Ethereum, they do it a way that kind of honestly seems not quite as good. I never thought that I would like Solana over Ethereum, but that sounds like a great idea. In Ethereum, what happens is you can keep your data there forever, but you do have a one-time incentive to clean it up, at least to clean it up when you're done with it, because you get part of your storage deposit back at the end. So those are two good ways to do it. I'm glad you mentioned that one I didn't know of. Yeah, go ahead over here.
And what does it mean to remove? How would you remove the data?
Well, I'm guessing it's a transaction, right? I'm guessing someone would send a transaction and they would say like, okay, the transaction says, take a look at this contract, take a look at its rent payment history. You can see that it's delinquent, evict it. And then it gets removed from the state, just like we talked about like,
With the other. Okay.
yeah, exactly. Yep, great question. Okay, yeah, Boda. Mic in the back. Throw the mic back there. Who's got the mic?
But then, if we allow this can cause like issues, like if other smart contracts are already calling this contract or something like that. But
That's like basically the trade-off, right? So that is exactly why Ethereum doesn't do it, right? I think you need to just have those semantics in mind when you're deploying your contract. So I've never developed on Solana, but I can already imagine like if I'm going to deploy a contract that relies on some other contract, there might be some kind of test that's like, make sure this thing's deployed before I call into it. Or maybe like if you call into a non-existent one, you get back some return code that indicates that or something. But yeah, I mean, you're exactly right. Like if one of your dependencies gets deleted, that's not ideal. But on the other hand, having all that junk in your state is also not ideal, right? So that's the trade-off. Yeah, so Bob is like, why bother cleaning this all up? And the answer is so that I can get a little bit of money back.
one question.
Oh, yeah, okay, go ahead.
Okay, I'm trying to fusion all the classes. In this case, it's not possible maybe that something like that could happen with the usage of the new block space design, but from the point of view of the real usage of a big company. For example, I listened that Deloitte it's intended to use the block space maybe with Kilt protocol. So it's possible that maybe this could I don't know fool the use a lot of blocks, and then this it's necessary then to remove the one of the Genesis block, create new Genesis more and more often, and maybe other projects that needs.
Wait, you're talking about new Genesis block? A new Genesis block?
Yeah.
Like
You say
launching a
that
new chain? You're saying like launch a brand new
You
blockchain?
say that it's necessary sometimes that move the Genesis block.
Yeah, so that process that I described earlier is called checkpointing, where you say like, I'm not going to sync the whole old blockchain.
Uh-huh.
Yeah, okay, I know what you're talking about now.
Yes. So if there is a very intense use of the block space, maybe it's necessary to move the Genesis block.
Okay, well, don't confuse the history of the blockchain with the state. So the state means everything that's going on in the blockchain right now. So it means everybody's cryptocurrency balance and every NFT and every like decentralized identity maybe that you're talking about. That's different from the history that says then Alice spent some coins, then Bob read his CryptoKitty, then Johan made a new DID or something like that. So checkpointing solves the problem of historical blocks. It does not solve the problem of the current state being big. You always need the current state, even if you prune all the old ones.
No, I'm talking about
Okay.
the transactions. If someone in another project that is a small company, maybe program a transaction in the long future, maybe that transaction will not be executed in the future because maybe the Genesis block remove the transaction.
When you prune old
from the
blocks
block
like
space.
that, so okay, if you do this checkpointing thing, you take the state, you take this, like, okay, let's say there's 10 blocks and I'm like, that's way too many, I'm gonna start from block 5 on. You can't just start with block 5 and an empty state at block 5. That would be inconsistent. The state roots would not line up. If you want to do a checkpoint, you have to have the correct starting state at your checkpoint block. You would call that like your checkpointed Genesis state or something like that. So even when you're checkpointing, you're still syncing and following the same chains. The state roots are still lining up. You still have the same state as all the other nodes. Okay, yeah. Mic up front. Or Carla, can you throw your mic? There we go. Right here, right here.
Please.
All right, don't want to go too technical, and you don't have to either. If maybe we can talk offline. But I was curious if you could maybe elaborate in terms of how this solution for state gas storage works. In Solana, it's completely, I think, different, where literally everything is wiped. So Solana doesn't have a notion of historical data, but on Ethereum, you do have like a historical record of transactions that you can always look back to, right?
I mean, so it's probably pretty clear that I'm not very familiar with Solana, but I would be like quite shocked to find out that they don't have a notion of like historical data. Like it's a blockchain, right?
Then we can talk about it afterwards. Yes,
I'm
just
I'm
curious.
not going to be able to answer
I'm just no, but I'm curious. In Ethereum, how does this work? Just a little bit more details. That's what I'm referring to.
I mean, it's very simple. It's not, maybe you're expecting something complex, but it's literally like I deploy my contract, I pay a lot of money to do it. Later, if I delete my contract, I get most of that money back.
Right. The transaction history is still there, though, right?
Well, yeah, all the historical stuff is there, but the state
right.
of that contract is not there.
Got
you
it.
never delete the old blocks, no matter what. That's like I would say that's like a main blockchain rule. Okay, yeah,
thanks.
over here. But give them their mic back. We're not stealing their mic. Who's got ours in the back, or the middle groups in the back? Yeah, huck it up here. You got it, man. You got it. You got it. Yeah. Go ahead.
Yeah, regarding the refunds in Ethereum, wasn't there like an issue where, contrary to what they were expecting, the state became more bloated because people were buying, like, storing empty data and then selling those refunds of gas to other users?
Yes, this was like an arbitrage of the gas price market, basically. Like, you store a bunch of baloney, you pay all the money to store it, and then
when it's
like
cheap.
maybe later when the gas price is higher, then you unstore it and maybe get back more money. I mean, that does actually add some efficiency in the storage market, but yeah, it actually made the bloat problem kind of worse in the short term. Very, very interesting tidbit.
Question.
Okay, last one, then I'm moving on.
Yes, I didn't get the concept really well. How can you delete a contract? It doesn't go against the immutability?
Okay, what immutability means is that, so we're telling a shared story, okay? First, Alice was born, then she ate breakfast, then she went to work. Immutability means that once we've agreed on that old story, modulo some concerns about reorgs, we won't unagree about it, okay? So that means I can never change the history that you deployed a contract and then you used it a bunch of times and then you deleted it. But it doesn't mean you can never delete it, okay? So think about it as like as a building. Maybe our story is like you bought some land and then you built a house on it and then you lived in that house for 10 years or 50 years or whatever, and then a tree fell on it and you demolished the rest of it. So the house is gone, right? It's no longer there on your property, but the history of that property still knows everything about it. That's what the blockchain does. The blockchain tracks the shared history, including everything that ever happened in the smart contract, all the calls that went to it. If you take immutability to this extreme, you guys are asking like, how can you ever change the state of the blockchain? That's not what it's like. How could I ever send you 10 Bitcoins? That isn't my balance immutable? Isn't your balance immutable? No, of course the states can change. That's the point of the blockchain. What's immutable is the history. Great questions. Okay, so let's get back to the game theory ones. Yeah, I talked through the storage issue, opportunity cost. This might be the last one I do because this is starting to be a long talk and I want to give you guys some work time today too. So opportunity is the loss of other alternatives when one option is chosen. Generally, when choosing between like $10 and $30, the opportunity cost of picking 30 is 10. It's the other option that you're foregoing. So that's opportunity cost. Ethereum state storage again. Yeah, so instead of having the funds locked into the storage deposit refund scheme, Bob could have invested them somewhere else and gained some profit, right? So it may seem that in Ethereum, there's no real cost to using all of that storage because, yeah, Bob had his tokens locked up there, but then later when he went off to play his guitar, he got all his tokens back, so wasn't all that storage free? Well, the answer is no, because he could have used those tokens to do any number of other things in the meantime. And so while it's the case that in Ethereum, you get back most of your storage deposit, but not all, you could make an argument that even giving back the entire storage deposit is enough because there's still opportunity cost associated with it. So don't tie this idea too tightly to storage in your head. It's not only about storage. That's the example I'm using. I think a better thing to realize here is that sometimes opportunity cost is enough. Opportunity cost is real cost. You don't always need to permanently take tokens from someone or have them spend tokens or burn tokens. Sometimes it's enough to lock up tokens. So there was this project called Edgeware that didn't get so huge as maybe some people thought, but it had this really, really interesting inception mechanism or like initial token distribution mechanism called a lock drop, where what they did was, it was kind of like an ICO, but you didn't have to buy their tokens with your ETH. You just had to lock up your ETH for a certain period of time. And at the end, you got all of that ETH back, but because of the opportunity cost, there was some value there, and so that's how they decided to distribute their token. I'm not going to do any more examples. So yeah, actually like, maybe a good example of an externality is what you were describing with the intentionally reserving storage. You know, like everybody knows that storage bloat is bad. Nobody wants Ethereum to be bloated, at least not Ethereum users. And nonetheless, as an Ethereum user, I might want to do this gas price arbitrage thing where I take up a bunch of storage only to give it back later. And because I personally gain an advantage of that, there's this negative externality that Ethereum gets bloated and makes Ethereum worse for everybody else. Not doing oracles again. So there are sometimes free transactions. For instance, in Bitcoin, after mining a block, you get a reward. This is a free transaction. It's not a positive externality. It's just inherent to the block. And usually, this kind of logic is something that has to be done like in every block. And so it's okay to not have fees on those. Oh, this is a good one. This is about Polkadot validation. All right, I'm going to do this one even though I'm getting tired and sweaty. It's about complete information versus partial information games. I think Jonas talked about this, right? Or someone did at least. So, okay. So to investigate this one, we're going to dive deeper into Polkadot and particularly into this like approval checking system or approval voting system, as you call it. And what you have to understand here is that there's these roles we know about validators, and some subset of them is like chosen to be approval checkers here. They're going to like check parachain blocks, basically. So in Polkadot, when new blocks are validated, not everyone does the work. Only some subset of them are chosen, and they're called approval checkers. So we assume that attackers can DDoS some but not all validators. This is like pretty reasonable. You know, maybe you have a chunk of money, you can buy or rent enough servers to do a DDoS attack and take out one validator or two or, you know, whatever, some finite number. But the validator set is pretty big and it's unlikely that anyone can, it's more expensive to DDoS a server than it is to keep a server online. So if you're running a DDoS, you'll usually run out of money before you can like DDoS them all. But that's okay. Sometimes taking out a couple key people is enough. Like Andrew explained earlier, with non-blind leader election, if you just DOS the person who's supposed to have the next block, that's good enough. Forget about the other 200 validators. We only need the one that's going to author. So similarly here, we might think about trying to DDoS some of these more key validators. So the way it works is that we like randomly select 3 of the validators to be approval checkers, and we announce who they are, and the approval checkers like publish votes, the ones selected. And by votes, I mean votes for whether this block that they're checking is good or not. And if all of the votes received confirm that the block is fine, then it passes. This is the happy path and what normally happens. Some block comes in, the 3 approval checkers check it, they all say it's good, it goes into the relay chain. So the thing is that we announced who the approval checkers were. And attackers use the information and DDoS the selected ones before they publish the vote. So if all the votes received, so we've got like, basically what we have here is an attacker who occupies some of the validator slots, okay? So in this case, they occupy one of them. Now, one is not enough to like mess up the results of this approval checker because there's 2 others in there. But maybe they can just like DDoS the other ones that were selected to be approval checkers. So let's ask ourselves, like, what was the problem here? And the problem is that the attackers learned everything about the game. This is a game of complete information. And so therefore they knew exactly who to DOS. So if we could somehow like limit the information of the game would change in our favor, it would be harder to know who you need to DOS. So we need to make it a game of incomplete information where some of the things are hidden. So the way we do it actually is kind of like how Andrew explained we solved the problem in either Babe or Sassafras, and we use cryptography, specifically a VRF, to generate these random numbers. It's kind of like a ticket. So validators with a sufficiently small number will have the right to be approval checkers. Hopefully this sounds familiar. It's very similar to how Babe worked, and validators with a low enough number had the right to author the block in the next slot. Approval checkers reveal themselves by showing their low numbers with the VRF proof, and they publish a vote at the same time. So now it's like blind voting, just like it was with blind authoring in Babe. This method has a nice property that attackers don't learn who the approval checkers are until they reveal themselves, so they can't get DOSed at all. Their vote's already out before you even know who they are. So if we had enough power to DOS 2 validators, the best we can do now is guess. And maybe sometimes we'll guess correctly, but in general, we probably won't, especially since the validator set is actually quite a bit larger. Okay. All right. I think I'm going to stop here, actually. I think that's as much value as we're going to get out of me talking. And feel free to read over these, and if there's something specific you want to see, I'll be happy to do it again tomorrow. So I think I want to take like maybe a 5 to 10 minute break, and I'll just sync with Alex to make sure we're all good on the assignment. And then when you guys come back, we'll kind of wind down with a nice easy work period, introduce the assignment, take any questions on that, and then call it a night. Sound good? All right, thanks everybody. Thanks for your attention. I know it's a lot of lecture right now.